Last event for the spring. We normally have at least throughout the year monthly events, and this is one of those. However, during the summer, everybody is on vacation, everybody wants to take time off, and so we don't hold the regular meetings, but we will still have some specific events that deal possibly maybe with training, Python, and on. So if you watch the calendar, you will see some of these events coming up, a couple of evenings here and there, and try and address specific topics. Apart from that, thank you all for coming. Now, naturally, one of the things that we kind of made a purposeful decision around is to ensure that we share the knowledge with the community. And with that, basically, we have been reasonably successful, and to that we thank you. We thank you for supporting us throughout. One of the things that we're beginning to, I guess, to face challenges with is possibly sometime venues. Sometimes it's too big, sometimes it's too small, it's too costly, and so on. So if you work for an organization or a company, or you know of a venue that we can at least access, or you can ask your company on our behalf, or you can introduce us. We try and give back to the community, and this is also something that many organizations they like to do. So maybe your company is prepared to do something for the community. But also, even for a selfish purpose as well, sometimes companies, they want to learn about advanced analytics and data science and business intelligence and what's going on in the industry. So this is also a way for them to have their employees without having to travel anywhere. They can just walk downstairs or wherever the conference room is. So if you know of, or your organization or your company does or is willing to do that, please reach out. We appreciate that. We can use your help. Now, other than that, tonight we're going to be talking about natural language processing. With natural language processing, one of the most difficult topics in data science is actually natural language processing, mainly because of the complexities surrounding each language. So, we all know, and many of us are multilingual. So we know that it's not a exact structure, especially in the English language. I mean, if there is anything, it's all about exceptions, right? There are so many exceptions in the English language. As well as a noun could be a verb, could be an adjective, could be a whole bunch of other things as well. So it makes it extremely challenging. And so naturally there is a different bodies of knowledge around that. And Dr. Molnar is one of the experts in that domain. One of the things that we've been collaborating on is to put together a short program, 2-3 days intensive training, and exactly directed to the NLP and text analysis and text treatment. And sometime probably in the next 2-3 months, we'll probably let you know when it is ready to roll. It isn't intended for somebody to start from the ground up. It's really a high level. So if you're knowledgeable in your language, maybe Python, maybe R. Yes. Dr. Molnar also will share another language with us. That it's something that you might be interested in. The other thing is that also, as a result of the presentation tonight, we'd like to hear from you. What would be a kind of an area of application, or maybe an approach, a particular approach to solving this problem would be of interest. Other thing that when we put out the information invitation to this event, we thought initially we will let you try on our platform, on Anova's platform, some of the coding in R or Python with the, for text analysis or sentiment analysis. But I think tonight, Dr. Molnar is going to surprise us with an alternative. So you're going to have some fun. We're going to try and play with the code, but not on our platform. It's an open platform available to anyone. With that in mind, please welcome Dr. Péter Molnár.
I know I didn't pay attention to the announcement, and I failed to send Frank something in time, partly because I think right now I just realized what the title should be. It's actually more, so I wanted to take you down memory lane. And one of the reasons is that we currently have so many new technologies, and there's a resurgence of virtually anything that has been touched multiple times, but just the time is right. We have computing power, we have data, and fresh minds looking at it. And so at the same time, I think there's a lot of old wisdom that was accumulated, and we want to preserve it, because we also see how these things potentially can come together. So nothing comes out of a vacuum. Even though the hottest thing that Google releases, probably if you leave down the seminal papers, the research that's built us coming from the 80s or maybe even the 70s. So I want to kind of use this a little bit as an opportunity to also to play, and with something that is sort of, it's not going to run on Kafka, but there is a history of, and it's actually, I think it's still pretty cool, and I think you can still take inspiration from it. So this is going to be like very high level, just natural language processing understanding, even though the terminology is very difficult. And maybe a good example. Thank you. Nice. And you've probably seen that in some form or the other on the internet the last couple of days. It just emphasizes how important natural language, how important it is to be precise. Otherwise, that's what's happening. So, I felt kind of funny. I saw some multiple versions of that. I don't know how to see them also. So, there's a lot of toolkits are out there. A lot of material which is part of this whole, I guess, democratization of data and computer science and AI, which is funny, it's like basically since we now the resurgence of deep learning, and which can also apply to natural language understanding and image recognition, image classification. So people are all excited about artificial intelligence. 50 years ago, people would slap you if you mutter that word. It's like nobody wanted to talk about AI. It's like, things come inside it, so just deal with it. But there are some really powerful toolkits out there, and that makes it, they're getting easier to install also, and everything is free. And what's more important is that most of these toolkits not just coming with the raw code and the algorithms, but actually come with data and pre-trained models. So this really allows us to be at the next wave where we can be consumers. There are language models for Arabic and English and German, and I haven't seen anything from Hungarian, so, but that's a difficult language. But so you even like Facebook has a package. I haven't played with it yet, but it's out there. Machine translation package already pre-trained with language models for different languages. So there's a good body that starts, a good movement that's going good momentum to actually diving in and being able, just like with, being able to do things that even a few years ago would never have the resources as a single company or an individual to even spend that kind of money and time to develop something, because we basically, yes, we can read all the academic papers, but we could not build it from scratch with our 3 developers. That's kind of really exciting, and hopefully it also made us rethink certain things that we might have thought about doing in the past, like looking at images or looking at text documents. I mean, text documents are usually archived electronically. That's very easy to do, but optical character recognition is so much better. But then what's next? We still, for the most part, use humans to actually have to read documents. So when I prepared this talk, I kind of went to my bookshelf and a little bit dated, but I think most of these books actually have new versions, new editions coming out, or some of them. So these are my inspiration for this, what I basically spent the last few days to go through. And I think they're actually really cool books. There is Juravsky and Martin is a classic, and they're actually working on the 3rd edition. The part of the book is available on that link. Manning and Schütze is also, it's a classic that's actually fully available, and still it doesn't have the convolution and recurrent neural networks in there. But other than that, a lot of the stuff that's really important to understand about natural language processing is still valid. So just because we have convolutional neural networks or recurrent neural networks, things get better, but some of the ideas don't just going to be thrown out, they're not obsolete. I'm kind of a fan of, let me say, I love Prolog, and Prolog is amazing. That's why we're going into history lane. There are not too many people in the US doing actually stuff with it, but one of them is a former University of Georgia professor, Michael Covington, and he just put, a few years ago, he put his body of work, his books out there. And this is a book that you can actually, it's scanned, but you can actually download the PDF. It's very nice. It does actually 2 things. It introduces Prolog it has an element in there, Prolog is a programming language. There are some books that he wrote about Prolog, but then he also, this is specific to for language processing. And this, I guess that's the old-fashioned way to do it. But you learn what it actually means to parse understand a syntax or a grammar of a language and try to solve those many challenges that we have. Because, face it, the natural language, the way we communicate, is probably the most lossy, noisy communication channel we can even think of. And somehow even, you might not even fully understand, maybe because of my accent and some echo in the microphone, but you still figure out what I'm saying. So it's kind of important in many cases, except for the first one that I showed. So, and then there is, if you're for Python in particular, there is a book that's also, basically had a print, might be still in print, but it's online. And they're updating, they don't update the book, but they update the online version. The NLTK book, that is basically for the Python version of the natural language program. And NLP was one of the packages. So, I hope that's big enough you can leave that. That's the abstract of, for me, that was I'm so fascinated by this book. That is the abstract of Terry Winograd's thesis in human-computer interaction. I don't even know if they use it that way. It's about Bloch's world, and he developed a system a natural language system to talk to a robot, and that was he finished his dissertation from 1971. In his dissertation, it's really interesting to read. He goes into detail how he had to cut corners to get, I think it's a PDP 11 or something, to get everything fit into memory. And he's also laying out that his limitations, memory limitations. But if you go to there's a website here. If you go to that, you can actually, it's just fascinating. You spend a few minutes and actually kind of look into, browse through his thesis, then this PDF format, and then look, this is an excerpt of an example diagram. But to go back here, the understanding that, and I think that is kind of key. I personally think it's key. You cannot do natural language processing without a context. We can, to some degree, and we have some success with that, but if you really want to go into the depth, get to the next level, so yes, we can do sentiment analysis on tweets, and we are probably 30% right, but it's to do the, to actually understand completely, and Delta not freaking out if I tweet worst day in my life landing on Delta, or taking updates of that. The worst day in my life, worst meeting ever, heading out, on Delta, going home or something like this. So then Delta Airlines shows up and everything is worst day of my life, and then they freak out, right? Even though it was not related, it was my meeting that was related. So this kind of things. So the context is important, and it's getting more important. I think we actually at a point where we can go back, pick out all this old stuff, and make it, probably combine it with the new stuff and make it work. And probably going to see more and more of that. Sure about that. So Schwindeloo, the Bloch's work. Schwindeloo is a weird name. It's basically the sequence of a typing device or something. We couldn't come up with something else. So I think it exemplifies very well what natural language processing needs to be. There's a language, there's a form and a grammar, and we have a vocabulary where we have a sense of the same, what words that we exchange have the same meaning, but we need to have a background context. And that's so in this case, it's a very small domain. The block of science, but have used it in other places. We usually use it as an example to for planning algorithms. If you ever had an algorithms class or something like this. So imagine a world that only exists out of the world, the universe is a table, and on this table are different blocks in different sizes, different colors. And you have a robot arm. That's this little thing. I think that's supposed to be the robot arm. And your robot can pick up a block and put it somewhere else on the table. So there's some action. So now, the way the system you interact with the robot is telling what to do and asking about the universe. So it's a toy problem, but it's a domain, a closed domain, and the computer or the system has an understanding of this universe. Excuse me. It knows if a block is sitting on top of another block, is hidden. So for example, if you ask the robot to pick up the red block that's underneath the green block, it will tell you, no, I can't do that, I have to first move the green block. And so this is an example. The software is still, I don't know if you can get it running, you can download it, it's written in this. Would be nice for somebody to create a blocker. So, But there's actually a long dialogue, and this is basically how it goes. So the whole project was having a computer and a human interacting and getting a task done. But it's only possible because there is a reasoning behind it. So the robot or the computer knows what blocks are accessible, which are hidden or covered, and where their position is. It knows what what an action would do if they are performing the task. So this slide, I tried to cram everything in. It is not comprehensive at all. So, thinking back that basically in the late 1960s, people were considering using human language to interact with the computers, and of course, the inspiration, the Turing test came even earlier than that. So it's a fairly early start. So what you see here on the, so what I tried to do is kind of bring different elements in and kind of break it down to some degree. It all started out basically with a symbolic representation. So we would think of our text, our words as symbols, and we have a sequence of symbols that then represent our language, our text. So there were dictionaries and grammars, and from that, basically, we're able to extract things like part of speech. So depending on where a word is in the sentence and what's around it, it might have a different function, thereby representing a different meaning. So the early days, the early decades of natural language processing were mainly focused on symbolic representations. Language models were usually handcrafted, manually handcrafted, and parsers also, because there are so many, there's a lot of complexity. People came up with a lot of different ways to parse them and try to find them to make it basically make the algorithm work and understand the actual concept behind it. The advantage of that is though that we actually had a real concept and real understanding at the end. It was very limited to some degree, but we have a lot of applications there. We might actually have a very narrow domain, but it still would be suitable. Plus now, of course, computation, and so it has been much bigger. Then, it's kind of losing the date here. In the 80s or so, people started stochastic modeling, word frequency modeling, and so on. So there was basically more data, more computing, and instead of focusing on creating what is the English grammar with all the sub-relative clause and stuff like that, and all the stuff, focusing on a statistical or stochastic model of language, like the probability that certain words occur in documents or occur next to each other and stuff like that. So that has been sort of an alternative approach, and so basically we can use that, often we can use that fairly successfully to classify documents. Because it doesn't really mean, we don't really have to understand what's in the document, but just the presence of certain terms make it pretty much more likely to be a document about this or a document about that. Some of the stuff like topic modeling can also be, but well, we can then, might even find out that there are certain documents that have a particular group of words that belong together, and other documents have a different group of words appearing often together, and use that to basically find out what are specific words that might be representative of a particular document. So we have a lot of these things going on. Basically, there's the term frequency sort of representation, which basically, I just want to know I take each word kind of out of context originally and just look at the frequency, how often it appears in the document. We can then step on, say, like pairs of words or n-grams of words or something like this. Alternatively, we have like the vector representation, which is, let's say, we take all our vocabulary and represent it as a fairly sparse word vector, the entire document, basically which words are in this particular document. So like bag of words, a set of words. And then not too long ago, 2012 I think, the word-to-vec paper kind of started a new era of embedding everything into a n-dimensional or k-dimensional vector space. So that is vector representation. That's, for most part, what's used in to feed neural networks, rather than the sparse, which is more, you can apply well for regression models, but not so much for neural networks, because you really just have zeros and ones. And also distances, between vectors or relations between words in these vector representations have shown out, like for example, that's one of the sort of surprising outcomes of word-to-vec, that you can almost do arithmetic on words because you have an embedding of each word based on documents that you feed in there, but it basically brings whatever dimension you do, whatever dimension you're in, you basically can use the Euclidean distance between two words to say how close they are together. And so I believe this was the first paper even, they did the WordNet synset, and I came pretty close to it. It was either that paper or something later, but not it. No, that they used the WordNet. So the WordNet, I don't have it up here somewhere. WordNet is a curated, basically, English dictionary. It's a huge database of, the Oxford Dictionary, basically, digital. It also has a thesaurus, or synset. So it has all the relations of what a word can be, whether it can be a verb, noun, or adjective, or adverb, what the different forms would be. Synsets are, for example, words that have the same meaning, like running, walking, so that's all curated. And that's another thing. So what we have on the left is pretty much all has been carefully curated by people and designed manually. Then the right-hand side of what we have here on the right-hand side is basically starting out, but we don't really care what each of these words are. We just take those strings, manipulate them a little bit, and then use these tokens to feed it in there without meaning. Which is great because some of these algorithms are kind of language agnostic. That's where you can actually train. And so it depends on the corpus. The corpus is the body of text documents. That's your data that you actually train with. And so depending what data you pick, you basically, if you use technical documents or legal documents, you basically create a language model based for that particular domain. With the availability of so many documents, particularly Google, for example, there was some time back, released, that was one of the first releases of big data and trained model was their Google Ngrams. After they went through all the digitizing all these books and scanning them in so that you can actually buy them and search for inside printed books, they used that to create Ngram models. And so instead of having to train it yourself, you can actually, for that particular language, also if it's for English, you can download it and use it for your purposes to, let's say, for example, predict correct spelling or predict the next word to type in, or even use that as a classification tool to, for your text documents. So we have these two sides. coexisted for a while. But at the end, we need to go deeper and have an understanding. And so that's why toolkits I showed you first, they all allow us to actually parse a sentence and understand each role or the part of speech of a word in that sentence. And now most of these models are a combination. There have been trained components in there. We're supported by that. So what we have now is actually these toolkits. We have very sophisticated models. Some of them is probably historically done manually, but then also a lot of the material it has been improved on trained models based on these background. So that's why I put this yellow arrow there to the left, because they actually work together. And what we have here is basically where we get down this road to create a way that we can have a machine taking the language and creating a concept that they can understand and reasons that basically we need to do. I know this is the longest slide. On top there, I just felt there was a little space left, since we're probably seeing it in one slide. We have different types of text documents, right? So we have a search query. If you go to Amazon and you want to have purple Reeboks in 11.5, yeah, you don't have to say men's apparel, footwear, sports, size here, you know, you just type it in and somehow it actually is pretty good. If they are purple Reeboks, you know, it might find them. Probably from the size, it might also start offering the men's shoes first before the women's shoes. There are some words. Some of these words have different meanings. They might represent an item, they represent an attribute, or they might represent a brand. So it's not that simple, but then the order is usually not controlled, because you usually just type a few words or you maybe speak into the phone. So there are certain criteria, so certain things might be, you know, we may not have to worry about. Probably doesn't make sense to do a grammar parsing on that one, because it's just about the words. Then we have tweets, or another quick social media stuff. Sometimes people actually tweet in full sentences, but that doesn't happen too often, and usually those sentences are also very simplistic. We come to messaging, so I hope you kind of see a little bit of where this is going. You know, typing an email or something like this, hopefully still people use real sentences. Language gets more complex. The vocabulary might also get a bit richer. Then we have blogs and news articles. There's still a few newspapers who actually have editors and write almost complete sentences and that you can read. But they also get much more complex. So you have like, you know, a sentence that goes over 3 lines and has like several dependencies in there, and like, you know, at the end it's like, what does that mean? If they say they, is that who does it refer to? That makes it much more challenging to understand what they mean, but then at the same time there's also so much richer what you can do with that, because there's some real information in there. So we can use news articles to actually understand what's going on in the world, and we can extract events from that and say, well, the president traveled to country XYZ and met with so-and-so. We can actually extract that from text documents if we, you know, with that. And then there's a big market, of course, in all kinds of different larger documents, like technical documents and legal documents and government reports and SEC filings and so on, where people have to, you know, often read through thousands of lines. And those languages are often very convoluted, and sometimes they might also try to want to basically phrase something. Let's say, think about a SEC reporting of a company or a report to the stakeholders. They might have handle loss, but they don't really want to phrase it that way. So then it gets really tricky to really understand. So you probably won't find the loss in there. So let's say you look for companies that don't do well based on the SEC filing, you might not be able to actually just pick out words that kind of tell you we didn't do well, or lost, had deficits or whatever. Should I find something better to say? So this is kind of the landscape of the whole thing. And I mean, yeah, there's no time to go into each of these in detail and spend hours with each of these things. And that's basically where we came up with this idea that maybe, because there's a lot of material covered, it might be good to kind of collect some material and create a workshop that is interest for that, because there's just so much to do. And functionality is there, but running examples for each of them or getting to be math, it's just not not possible to do this here. But there is a use for many of these things. So even though we have some sophisticated algorithms doing something, sometimes you might still, your domain might be so small or so different that you might actually have to go more back down to the basics and rethink things. So not always just taking something out of the box and let it run. Even though that's possible, and in many cases it works too. So that's why I kind of want to go a little bit down and the memory thing. Actually, basically, this is kind of very generic, and let's put this together. But there are a lot of terms in here, and actually just want to sort of, this is like a typical pipeline, the way we grow. And if you think about matching this with the tools that you use, you don't have to use all these things, because like if I have a tweet, I'm not going very deep down and try to analyze the grammar structure of that. Even though Twitter has sort of certain conventions depending on where you put your ad and hashtags, you put them at the end or at the beginning or the middle. Apparently there's some meanings with that, but that's convention, and of course you can find out. But and out, by the way, these are later in a few slides you see a GitHub link, and the slides are on GitHub as well as the programs that I put together. So it always starts out, of course, we have a text document, we have to do some string manipulation to kind of bring our text into the right format. And so the first stage of every analysis is basically on the word itself. There are different things we can do in terms of, for example, cleaning out different ways to spell a word, or even sometimes abbreviations that are commonly known, like United States or US and stuff like this, or certain apostrophes which always kick you out if you just use a regular special character division on your token, to break on your text. Because you kind of need to clean up extra spaces, tabs, what do you do with an exclamation mark, finding this the end of a sentence and so on. And it very much depends. So if you, for example, have like O'Neill's in there with an apostrophe, then that's different than if you have the owners, with an apostrophe as a genitive as opposed to plural. The owner's car. So you have to be careful with that. It is not quite trivial, but then you have tools for that. So that's one of the first things we want to do. And then on a word basis, we might also, depending on what we're looking for, we might want to stem a word. We don't really care about walking, walked, walked, walking, walk, or something like this. It's the token is supposed to be, okay, something is moving. So we might do this. And there's stemming and lemmatization. Lemmatization is basically going proper after the dictionary. Let's say, for example, you have mouse and mice. You can't really. So the stem is usually the beginning of the word, which often doesn't change, and then you have the ending. And often it's good enough you just chop off that part, the ending, and you keep the word. But sometimes you might have to do this in translation. Then after that, it's basically where the syntactic analysis comes in. So how does this fit into the sentence? And that's pretty much the same as if we write a expression in any programming language. There's even more structured syntax, and most of these ideas come basically from the same way. So we actually often treat, or particularly early beginners, languages were treated as formal languages. The same way a programming language was treated. Programming languages have less ambiguity, but the process is kind of similar. After that, we're basically assigning meaning to that, semantics, to really actually understand and extract the concept. What is going on here? What does the sentence or this document describe? And then kind of going from there. So I have, but I think it always takes more time, right? How much time have we spoiled so far? 30 minutes? One example, sentiment analysis, because Frank and you might actually have something else. So there's a simple way to do that, which is basically actually just looking at a bunch of dictionaries that are basically provided. People did research and created good and bad words, and that's something you can use to kind of get a sense of what the sentiment of the document is, or the sentiment of the people. Sentiment analysis in general can be much more dimensional than just good and bad. But what we do is we try to express a polarity of anything. So it could be, if it's about restaurant reviews, you might have a polarity just good or bad. But there might be other emotional scales that, like aggressive, defensive, and so on. So there's actually a whole body of work out there that is like, messages are more threatening. So it actually, particularly for social media, it could be different types of how different polarities. So basically, two ends of the spectrum of something we kind of try out. That would work pretty well. There are also methods, if you kind of know, it kind of goes along with classification. If you know certain documents that are bad, certain reviews that are bad, certain reviews that are good. Often, if you download the Yelp data set, for example, you also have a star rating. So it would be unlikely that somebody gives a raging positive review and then gives only 1 star. So we might use that to kind of start training. And then it comes down to looking at words that appear more frequently, for example, the bad reviews versus words that appear in good reviews. So because of that, there's a nice collection of on that link that is from on GitHub about some sentiment data, if you're interested in that. And here's some examples. I hope you can read that. It's these are some. The first ones are easy. The bottom ones are difficult. So the best lines of all the day cruisers, it seems to be there's a Coronet, I guess it's a brand. Easily is a very positive word. Ugly is a very bad word, and dislike and old are probably, both kind of have negative quantifications. So these two sentences are definitely would be, considered more negative. But then if it says like, I don't dislike, and that's what our language can do. We basically turn the same word, meaning of the word around by just negating it, or we add other things to it. We might be sarcastic, and it might be sarcastic command, or just like, it seemed to be, comments like, I hate this room, I hate, basically what I say, I hate I hate your shirt, even though I like it. So people do kind of say this kind of things. Yeah, for us who are not native speaking, this is always getting more confusing, right? So anyhow, so getting up is get quickly, you get like a good portion, but then to get to the next level, it's going to be very, very complex. So one paper I found is actually addressing that issue. That's a pretty, if you make, you might recognize some of these names on that paper. They're actually like, okay, how do I get the last mile in sentiment analysis? And it ends up basically creating a path tree, and I'll show you more of those. I actually have to go back and understand the entire sentence structure and then figure out what part of the sentence is negative and what part is positive, and is there, for example, a negation or an opposite. So if I hate Coke, but I love Pepsi. If I have those things in there, need to find out what is, how they're associated. So at the end, if you go back to, if you still remember my big chart, go back to the old-fashioned. We need to understand the path to at the end. Fortunately, that's gotten so much easier, and we don't have to manually create those trees anyway. But I think it's good to at least have like an idea about how these grammars look like. What is a grammar? And some programmers, you might actually have seen that. We use the extended Bacchus-Nauer form to document programming languages. Now, coming and I think Pascal books, just like really back in the days, used to print the syntax in the EVNF. Any of you ever bought the first copy of the Cunningham-Ritchie C programming book? Yay! Did you have the poster in the back? There was a little, some copies there was like a little fold out, like a paper you fold out, and had the entire story. Well, that was not it was not this format, but there was an entire chart of the entire syntax of the C language on one sheet of paper. So that was when we were not used to having a semicolon at the end of any statement and stuff like that. Anyhow, so one way to describe grammar is to basically formalize what a language is, the shape of it, the format of a language is to define a grammar or a syntax. And we do this in saying we have a sentence, and this sentence can have different components. And so we create a substitution rules. That's what you see here, you can read it. I might have a sentence that has two parts in there. That means A and B. And so the my string, my basically sequence of terms, or I can substitute them with a different symbol. Or I can go the other way around, saying if I have a sentence, I can convert my sentence and produce another sentence or another sequence of symbols that have that shape. So you think about substitutions, and then if you think that, hopefully I have this one, you can think of this as a tree. And it can go basically both ways. And so what we have in a grammar, we have rules, and these are basically have a certain format. What I can, on the left-hand side, can be substituted with what's on the right-hand side. And then we have different types of symbols. Our terminal symbols is actually the symbols of our sentence, or in this case, our vocabulary. So we think of individual words, one word is a symbol representing something, not the character. So go to the word level. These are terminal symbols because that's actually at the bottom, that's what we feed in. Or you can also think of like, that's what you produce. And then we have non-terminal symbols, which are basically in between symbols, you can take some of these symbols, combine them, and let's say, for example, I will give you some example later. So basically, I might have a symbol that in the English language, for example, presents a noun phrase. That's usually the phrase that represents either a noun or an adjective in a noun or a determiner in a noun. And so then I can introduce different, my grammar, I can introduce different non-terminal symbols that are help me, that basically replace some symbols and then assemble them. And what I want to do, if I have a sentence that starts out with only terminal symbols, because that's basically my vocabulary, can I replace those to get to, using these rules, to get to the root, the sentence. And if I can do that, then my sentence is grammatically correct. So it basically describes a pattern, and everything that can basically fit this pattern with multiple substitutions is able to, is basically is part of my language. So the simplest one is here actually, what you see on the right, is you have all the capital symbols that start with a capital letter are non-terminal symbols, so they're basically virtual matter symbols. And my vocabulary here actually only consists out of two terminal symbols, and those are A and B. So what this very primitive grammar says is that, and it's a little bit more complex, that basically I can say my sentence can be replaced by a capital A, capital B. So two parts of the sentence. One is capital A, one is capital B. And if I go down, my capital A sentence is actually, can be the symbol A, lowercase a. I know, it looks good on the screen, but if you talk about it, it's, uppercase, lowercase. But or a full sentence. So I have a recursive relationship in there, which means that if I have a sentence and I add an A in front of it, it's still a sentence. So, but actually it becomes A. So if I have a sentence, so the sentence and add an A to it, it becomes an A part. And then my B is actually, the capital B can only be replaced by a single B. The solution is there, but that's basically what this somewhat primitive grammar says, is that I can only create strings that are AB, AA, BB, AA, BB, and so on, so basically equal parts. Sounds more complex. Actually, that's why we actually go to you hanging with me here to play with prolog a little bit, because actually we can do things like this, almost literally using that. So this kind of notation. So this is like the formal concept. That's how I would define a programming language. This is how I would define how a numerical value, a literal, let's say a floating point literal, would be in my programming language. I would say there's some digits, and I would say what digits are. I would say there is a decimal point that I allow, but I only allow one in there. So I basically create a rule that would only allow me to have one decimal point either in that whole sequence of digits, and then it might stop, or I might have an F or E or something in there, and then I might have another sign, plus minus, and another couple of digits in there. So that part would be defining the language for a floating point. Then I would apply the same things for the structure of a function and so on. So we basically do the same thing to the English language. And I pointed some different things. So basically, here's like a very toy example. Noun phrase, verb phrase. So basically, every sentence in the English language, when I started, we learned SPO, subject, predicate, object. So much easier than in German, where you can have the object first and the subject at the end of the sentence. but the predicate in German always has to be in the second place. There are other languages where you don't have any conditions, and so that becomes like basically it's up to you what you want to express or what you want to stress out in order to how you want it to words in a sentence. So that's all interesting challenges. So here's like, maybe this is something you can read this, but you can also, maybe it's very unfamiliar, go back. So we have, so this is basically how this sentence can go back. So what we have is like, this is our sentence here, and I prefer a morning flight statement. Is that a valid sentence? According to these rules here, my vocabulary is up here. I have each of the non-terminal symbols on the left can be substituted by any of these terminal symbols. So I group them in verbs, nouns, adjectives, pronouns, and so on, proper nouns for names and stuff like that, prepositions, conjunctions, etc. And then I can start creating rules. What is possible to say? I can't put an adverb in front of a noun, not allowed. But I can put an adjective in front of a noun. Sometimes they're actually the same, right? So it's hard in English to explain it. So it's a flight, it's not flight A. That would be something totally different. And every time we can produce, so basically we can apply. So basically we assume there's an algorithm, our parser, that can apply these rules to make this sentence. And that is not trivial. It very quickly becomes very complex. So this is also, these are very artificial sentences. It's the same sentence. Our company is training workers. Not much to it, right? But with everything, in computer, for them everything is equal. They actually find out there are different possibilities. So we have a lot of ambiguity in here. Our company, the noun, that's the subject of the sentence, is training workers. So it's training workers is the verb phrase, and that's the auxiliary, that's the gerundium. Our company is training workers at the B. What does that mean? It has a different meaning, probably is possible. I mean, we could use company in a different meaning, right? So, yes, exactly. So they're basically, we are the company of training workers. Our company is training, I guess, as an adjective. What is that adjective? Consists of training. Yeah. Purpose. The company is training workers, yeah. So that's so basically different meanings, same sentence, and all of them are valid according to this number. At that point, that's where we come to the point where really a understanding of the context needs to be in the background. And there might be some reasoning that maybe we say our company, there's already something in there. We're actually talking about a company. So let's say our company has RentPath, and then okay, with that, number B would be, and maybe even C would be out of the picture. So Noam Chomsky might have been the same one who's also a political critic and very vocal. He's also a linguist, and he created, and there was a time basically going back in history, memory lane, a time to try to formalize and create an overarching theory or theoretical body for all languages. And I think since then this kind of has been abandoned. I think we're no longer really aiming for completely describing human language. Now it's just like, whatever, that's usually what we see. But it might also be changing, so these rules, even if you think about it, our language is constantly evolving, and just because something is not grammatically correct today doesn't mean that people start using it tomorrow. And then, if you